Gordon Richards, who is coming to us from Philadelphia, Drexel University, on Thanksgiving. So we have to be especially thankful to Gordon, of course, for agreeing to speak to us today. So, as I said, he's currently faculty at the University of Drexel in Philadelphia, but originally received his PhD from the University of Chicago and has formerly held Sloan and Moore fellowships, I think. I don't know if that's the right way to term them, but anyway, at Princeton and Johns Hopkins. So Gordon is a leading expert in all things quasar, and that's what he's going to talk to us about today. So I'll just hand immediately over to you, Gordon, and please take it away.
Great, thanks, Tom. All right, let's see here. If I can get this to work properly. Everybody see that okay?
Yeah, that's good.
Okay, great. What I wanted to try to do today is give you what I think of as sort of a modern picture of quasars. And you'll see what I mean by that as I go. I need to thank quite a number of people at IoA Cambridge as listed below, and various collaborators from around the US and around the world over the past few years that have contributed in some way to the slides here. And so I'm going to take a bit of a risk and try to combine the major parts of like 3 or 4 different talks into one. In part because I want to think of this as not a talk, but as like the start of 12 different conversations that I would like to have with people there the next time that I'm able to visit, which I was honestly thinking was going to be this summer or summer 2021. We'll see if that maybe is too soon. I am happy to take questions as we go. If I talk at my usual speed, it should be like 50 minutes. If you want to interrupt me, that's fine. I can check every once in a while the chat, although I'm not that good about keeping track of it. But if people have pressing questions, feel free to ask. So I'm going to spend the first bit of the talk talking about quasar physics and spending a little bit of time talking about the origin of radio emission in quasars. And then I'm going to sort of switch to talking about, basically what we need to do for the next generation in terms of getting the most out of LSST and next generation surveys. Okay, so I always like to start at the beginning, even if the room, as it were, is filled with experts. And so let's talk for a few minutes about what quasars actually are. So quasar is just a galaxy. It's a galaxy where you have a supermassive black hole that's actively accreting new material. That accretion disk is about the size of the solar system, sort of from Uranus out to maybe the Oort cloud, depending on the size of the black hole. And that accretion disk is emitting light, or causing light to be emitted over really the whole electromagnetic spectrum, and dwarfs the light from the galaxy itself. So this artist's rendition is sort of zoomed into the very center of the galaxy here. I have a tendency to equate all of these terms here: quasar, QSO, active galactic nucleus, AGN, CFERT, and so on. There are real differences between them, but the bottom line is they all involve active accretion of material onto a supermassive black hole. For the most part, I will be talking about sort of bona fide quasars or QSOs, that is, things that have luminosities of 10 billion to 10 trillion times that of the sun, and black hole masses of something like 1 million to 1 billion times the mass of the sun. And I always find that it's kind of fun to juxtapose the efficiency of black holes to nuclear fusion in the sun. So nuclear fusion in the sun is something like 0.7% efficient, whereas the black holes are like 6 to 32% efficient. Oops. Okay. So quasars can be fueled in a number of different ways. For the masses and luminosities that I'm largely going to talk about, we think that they're largely fueled by mergers of galaxies. And so the idea is basically illustrated in this slide here. So you're going to merge 2 gas-rich galaxies. That's going to form a buried quasar in the sense that the gas loses angular momentum and is accreting onto the black hole. And feedback is going to expel the gas, where that feedback can take a number of different forms, but and end up revealing the quasar. And the way I usually describe it in talks is it's sort of a warped murder-suicide process, right? So the quasar itself is sort of blowing out the gas that would have formed the next generation of stars and would have otherwise, made this a blue elliptical galaxy instead of a red dead elliptical galaxy. And that's also the gas that was going to keep fueling the quasar and causes the quasar itself to shut down. And so this is, work that's been going on for 20 years, including at Cambridge. And so that kind of sets the stage for the rest of the talk, in the sense that, it's important to realize that quasars aren't, unusual objects. They're sort of a particular stage in the lifetime of essentially all massive galaxies. All right, so if you've ever been to a quasar talk, you have seen this picture from Uri and Padavani. And so I would argue that we should really stop showing it, because nobody thinks that quasars look like this. All right, well, maybe they do, but when it comes down to it, I would say that we don't. But it's a useful starting point to talk about some of the empirical features that we're going to see. And so this is the spectral energy distribution of quasar, so the light output from the radio to the X-ray. And what we find, is that about 40% of the light of the quasar is output in the optical UV. That's actually coming from the accretion disk itself. That's this sort of pink region here. So it's a multi-temperature black body, and you get sort of a modified black body kind of shape here. And then another 40% or so of the light output is in the infrared, from the near infrared to the mid infrared to the far infrared. And that's coming in this cartoon from this so-called dusty torus, which I would argue is more like the part of the wind that I'm going to talk about in a few minutes that's past the dust sublimation radius, but we can think of it like that. The host galaxy that these things live in, so we're zoomed into the very center of the galaxy here. The host galaxy is something like this. So this is sort of a composite of many K stars, sort of peaking at 1 micron. And the important thing here is to note that the quasar is completely outshining the galaxy at basically every wavelength, and by a factor of 1,000 or so in the UV. The last sort of 20% of the spectral energy distribution comes from the X-ray, where the corona, this X-ray corona, can take multiple sort of different shapes. So either as sort of this sort of spherical region around the black hole, or maybe the skin of the accretion disk, or maybe all of those things. And so that's an extremely important diagnostic of quasars as well. I will talk about radio emission a bit. So what's interesting is that only something like 4% of quasars are emit in the radio. And so you can see even the ones that do emit very strongly in the radio, the total energy generation is far below what it is in the optical and the infrared and the X-ray. And so we'll talk a little bit about what may form these jets. And then if I zoom into the optical UV region here, where this upward slope here is this sort of downward slope here, just to be annoying, I've switched units from energy to wavelength. And so what you see here is the strong blue continuum of the accretion disk, and then superimposed upon that are these strong emission lines. So there's these broad emission lines coming from so-called clouds of gas that are deep in the potential well. And then there's the narrow emission lines that are coming from clouds that are further out in the potential well. All right, and so that's sort of gives you the landscape of the kinds of things that we are going to be looking at in terms of our multi-wavelength data. So one of the most important things that you have to know to understand quasars, particularly at high luminosity, is this. So the spectral energy distribution of quasars doesn't scale self-similarly with luminosity. So what do I mean by this? So here is a cartoon of the spectral energy distribution of a relatively low luminosity quasar, where I've basically just shifted all these curves down by a bit. And what happens is, if you increase the UV flux by, say, this much, you get this SED here. And the thing that happens is that the X-ray doesn't go up by as much as it sort of otherwise should have. That is, if we increased the UV by, whatever, a factor of 500 or something here, the X-ray doesn't go up by a factor of 500. It goes up by something less, right? And so it's not scaling self-similarly. Another way to see that is this plot of so-called the LUV alpha X relationship. So this is the UV luminosity, and then alpha X plotted here is the slope between the UV and the X-ray part of the SED. And so if the SED scaled self-similarly, this would be a flat line. That is, if the UV went up by a factor of 100, the X-ray would go up by a factor of 100. And you see that's not what happens. So as you go to higher and higher UV luminosities, the X-ray does go up still, but not by as much. And that is really crucial to understanding what goes on with quasars, particularly winds being driven off the accretion disk. So when you say AGN, here's what I think of, right? And so one of the things that I want to try to impress upon you is that one of the reasons I don't like to show that Urian-Padovani picture is it gives you the impression that all quasars are alike. And while I'm going to argue that quasars are sort of a continuum, it's useful, I think, to think of them as sort of two extrema, even though the average object is sort of somewhere in between, because then you sort of realize that they're not all the same, right? And so when you say sort of a low luminosity AGN, this is the picture that comes to mind. This is from Conical and Karcher, 1994. So you have a multi-temperature accretion disk here, where I've drawn a mostly polar sort of MHD wind. And so the idea here is that if you look down the line of sight so that you're seeing the accretion disk, we're seeing into the region where you're producing this sort of modified black body continuum. That's this strong continuum here, which isn't properly normalized, but you're basically seeing into the accretion disk. That's evidence of that here. And then these broad lines here are also seen when you have that point of view. And so this is your sort of classical quasar spectrum. And then there's clouds of material, which I've drawn here as actually threaded on the MHD lines. So what's important here is that the clouds that are out past the dust sublimation radius, so these are dusty clouds, if you are looking towards the very central engine of the black hole through those clouds, then you're basically obscuring that the optical UV continuum, and so you don't see much continuum here, and you're also obscuring your view of the broad emission lines, and so you just see the narrow emission lines, which have a scale height that's much larger than the dust in the wind here, and so you get an obscured or type 2 quasar. All right, and so I always describe it, this is sort of your fiat of quasars, right? It gets the job done, but it's nothing fancy. So then what happens is when you scale up the luminosity, you get really a very significant change, because you are increasing the UV more than you're increasing the X-ray. And so I'll walk you through what how I like to describe what happens here. So here's my accretion disk again. And so remember, it's got a range of temperatures, sort of soft X-rays towards the center, where it's hotter, optical towards the outer edge here, where it's cooler, and then UV, lots of UV in the sort of the middle region here. And so our accretion disk isn't solid like I've drawn here. It has sort of an atmosphere, and that's made of normal stuff, carbon, nitrogen, oxygen, and what have you. But with a few less electrons, because there's enough ionizing photons here that you're going to strip off some electrons. And so even with those atoms ionized, at least partially, you have lots of UV photons that are going to cause transitions in the UV part of the spectrum. That is, photons coming in, they're going to excite an electron, jump up to a higher energy level, and that'll eventually fall back down and produce an emission line, right? And so we have lots of UV photons coming from the disk and lots of UV transitions to excite. And so what ends up happening is that you actually can blow a wind off of the accretion disk. So this the force from this sort of radiation line driving is actually quite strong. So the cross section is something like 10 to the 7 times that of electron scattering. It's comparable to the solar wind. And so, essentially what happens is that the radiation is imparting momentum on the electrons, at least the ones that haven't been stripped off, and they're dragging the nucleus with it, and then you get this wind blown off of the accretion disk, which is kind of counterintuitive. You would think that this supermassive black hole is gobbling everything up, and it does. But if you can avoid, if you can basically produce lots of UV photons that are going to drive this wind, and not very many X-ray photons, which would otherwise over-ionize your atoms and basically strip off the electrons that are going to sort of be doing the work of driving the wind, then you can have this sort of weird situation where a wind's driven off of the accretion disk. And one of the reasons we know that is these so-called broad absorption lines that are seen in the spectra of, some 10 to 40% of quasars, depending on how you look at them. So these are signs of a wind being blown off the accretion disk, and we think that what's happening here is you're probably looking down a certain line of sight where you're catching the wind is basically obscuring some of the light that otherwise would come to you. All right, and so this is your sort of Ferrari of the AGN world, right? So these are the sort of the monsters, right? And so you can, so these winds are potentially really important, and like I said, so it depends on how basically the UV to X-ray flux ratio. So one way that I think is really good that has come out recently to illustrate this is this paper by Giustini and Proga. So this plot is basically showing sort of more moderate accretion rate sources, sort of Seyfert objects with here luminosities 10 to the 43 to 10 to the 46. And in this plot, the pink is showing the corona, both in the cartoon and in the SED here. And the green is showing the accretion disk, again, both in the cartoon and in the SED. And then these lines are showing a wind being driven off of the accretion disk. And these sort of blue squigglies are where the wind has failed, right? So there's not enough radiation line driving happening, right? So you've got maybe too many X-ray photons stripping the electrons off the atoms. And so what happens here, where you've got relatively low accretion rate and low mass, is so the UV photons are over here and the X-ray over here. So you don't have very much UV, you have lots of X-ray, and so you have a hard time driving wind. But for that same accretion rate, if your black hole mass is higher, that actually cools off your accretion disk. And so this part of the SED sort of shifts over. And so now you're putting out more photons from the accretion disk in the UV, and your X-ray is basically staying the same, and you're able to drive a stronger wind. So when you increase the accretion rate, right? So these are sort of typical slow quasars, sort of luminosity of 10 to the 44 to 10 to the 48. So these are, narrow-line Seyfert 1s and BALs and so on. Now the accretion disk is basically better able to cool the corona, and so two things happen here. So our accretion disk is overall a greater contribution, making a greater contribution, and the X-rays are reduced, and basically the slope of the X-ray changes. So you have fewer hard X-ray photons compared to soft X-ray photons. And so we're able to drive a stronger wind, and even stronger wind when we have high accretion rate and high black hole mass, which shifts this bump over from the accretion disk into the UV. So now we have lots and lots of UV, not very much X-ray, and we can drive a very strong wind off the accretion disk. Right. At the highest Eddington ratios, so we're here, the Eddington ratio is basically the bolometric luminosity divided by the maximum luminosity that you could have for spherically symmetric accretion. Basically the standard thin disk model from Shakir and Shanayev from the 70s is known to break down. And so there's this slim disk model that goes back to Abramowitz 1988, where the use of the term slim here is different from what I think of, but the idea here is that instead of this thin disk, you have this sort of puffed up inner region. And in both of these cartoons, that what's effectively happening is that you're blocking X-rays from getting to where these broad emission line clouds are. And so you're not stripping electrons off of those atoms, and you have lots of, but the UV photons are able to get to them and drive a strong wind. Okay, so how do you know if you have a Fiat or a Ferrari? That's easy in some ways. So here we're going to do that with a principal component analysis. So these are composite spectra derived from a principal component analysis. Basically, trying to find trying to compress things into 2 dimensions that maximize the variance in our spectral features, and then basically making a composite spectrum of them. And so this was novel in 1992 when Borison and Green and Francis and Hewitt first did it, but it's pretty common today, right? And so what we can see here is that there are empirical differences in H beta and O3 and iron 2, and those are revealing critical physical differences. And so what I like to emphasize here is that it's pretty hard to measure masses and accretion rates for individual quasars, right? So SDSS has confirmed about 500,000 quasars. We are not going to accurately measure masses and accretion rates, and never mind black hole spins for all of those objects. But these emission line properties encode that physics, right? So I can't tell you necessarily what the accretion rate and the black hole mass are here and here, but I can tell you that the black hole mass and the accretion rate are very different here and there. Okay, and so these are your sort of Fiats and these are your Ferraris. And so even if we can't measure physical properties, we can still do real physics. All right, so the problem with these lines here is that they're available to us at in the optical for only low redshift quasars, or if we do a lot of work and take infrared spectra. And so we have to move to using these lines here, carbon-4 in particular. And so we're specifically going to use 2 properties of the carbon-4 emission line, the blue shift, which I've shown here on the x-axis, and the equivalent width on the y-axis. And this little inset is illustrating what it is that we're measuring. So the equivalent width is just the integrated area under the curve. And then the blue shift is basically a measure of how shifted this peak is relative to the laboratory wavelength. And you see, there's not a one-to-one correlation here, but there is sort of an interesting trend, and there's sort of this quadrant of missing objects up here. So what I didn't say with that plot is that the red contours here are radio loud sources, and the black contours are radio quiets. And I've also labeled broad absorption line quasars down here in the bottom right. And so a number of researchers have argued that this is basically a trend in L over Eddington, right? So these are low accretion rate relative to their mass, and these are high accretion rate relative to their mass down here. So there's a trend from lower L over Eddington to higher L over Eddington as we go from one side of this parameter space to another. Whoops. So I put the broad absorption line quasars down here. So those are objects that have really strong winds. So you can think of this as sort of weak winds to strong winds as we go. But that's not saying that the broad absorption line quasars just live down in that corner is not quite true. And Amy Rankin has a nice paper that recently came out showing that you can actually find broad absorption line quasars everywhere in this parameter space. But what's crucial is that the character of those winds of those broad absorption troughs changes as you go across this parameter space. So in this bottom right-hand corner where said the broad absorption line quasars were, that's where you find these whopping troughs that are indicative of very strong energetic winds. And then the broad absorption troughs that are sort of up here perhaps aren't as strong. All right, and so I basically showed you how we can use two parameters from carbon-4 as a diagnostic of our wind. And so one thing I want to emphasize here is that the properties in carbon-4 are very highly correlated with some other features in the emission spectra that we see, particularly this helium-2 line and this carbon-3 complex over here. And so if we can use information from these other lines, then we can basically place our objects with an even greater degree of accuracy. And so the way I like to describe that is these are composite spectra where the red are small blue shifts and large equivalent widths. So that's the upper left-hand corner of the plot that I showed you. And the blue are large blue shifts, small equivalent width, the lower right-hand plot. And so these red objects are going to have lots of ionizing flux. I'll talk about the radio in a second. And they're relatively unlikely to be have sort of these whopping broad absorption line troughs. Whereas the blue are the opposite. So they have less ionizing flux. They have a lower probability of being radio loud, but are much more likely to have these sort of whopping broad absorption line troughs. And so what we think is that is sort of largely a trend in the spectral energy distribution. So this is a suite of SEDs produced by Karen Laley back in 2007. And so the gray here are quasar SEDs where that are what we call very hard, right? So there's not much UV, there's lots of X-ray, and then there's basically a continuum going to the black here where you have lots of UV and not very much X-ray. Whoops. And so what we find here is something that's nicely illustrated by another plot from Amy here, where the helium-2 line is actually a really good diagnostic of what kind of SED you have. So that's basically a measurement of the equivalent with this line right here. And you can see there's this nice continuum going from the upper left to the lower right. And so basically what we think is happening here is that these objects have so-called hard spectra SEDs, and these have softer SEDs. And so these are less able to drive a wind, and these things are more able to drive a wind down here. Okay, so what we'd like to do is put quasars onto a main sequence and mass, accretion rate, and spin. That's hard, right? Because we have a hard time measuring those properties for individual objects. But I would argue what we can do today is put them on, sort of an empirical main sequence that's guided by these bulk emission line properties. That is, we can compare quasars that have very different black hole masses and accretion rates, even without having measured those directly. And so the next thing I want to do is talk a little bit about how we can use that information to learn something about the origin of radio emission in quasars. And so this is an example of where I basically am sort of switching talks. So, but I think this is really interesting. One of the things that fascinates me, and I would love to talk to people more about. So, so let's start with what we've learned about radio emission from quasars in the past 50 years. Frustratingly little. So that's not fair. But you'll see what I mean in a second if you sort of bear with me, because it helps set the stage. So for example, we have evidence of very strong extended radio emission, which are pretty clearly from jets, but we don't really know what causes the jets. And again, you might say, yeah, Gordon, we know what causes the jets, but in a way, we sort of really don't, right? We know it probably has something to do with tapping the spin of the black hole or the accretion disk, but I'll show you in a second why I think we still don't really fully understand that at all. And then there's weak radio sources where it's not obvious that the emissions from jets, and so it may be that it's a star formation. It could be these winds that I've been talking about slamming into the ISM and producing shocks and that producing the radio emission. Could be the coronae. It could be sort of smaller scale jets. It's not clear. And so let me walk through a couple of those things, right? So in terms of the radio loud quasars, so this is the sort of the tail of objects that are probably dominated by synchrotron emission from jets. So the classical number is that 10 to 15% are radio loud. So this goes back to a sample of about 100 or so quasars, you know, from the sort of so-called Palomar green sample. And so that fraction has not sort of stood the test of time as we go and observe fainter and fainter objects. So the detected fraction of quasars in the Sloan Digital Sky Survey is only 4%, and only about 10% of those have extended morphology, right? So I said, you know, we've taken spectra of about 500,000 quasars, and so there's fewer than 10,000 objects that have a strong radio emission that we can ascribe to jets. And so that's pretty frustrating. This is, I'm back to my carbon-4 plot here. One of the things that we would like to know is, can we use the radio morphology and basically the orientation that information that we get from that to learn something more about what's going on here. So that is, you might expect core sources are, and this is sort of a lesson in radio astronomy that is again, you know, part of another talk. But if you just see the radio core, the idea is you're probably looking down the jet, and if you see sort of the lobes, and then you're maybe sort of looking edge on, and so the radio morphology might tell you something about you know, orientation, and whether this diagram isn't just the accretion rate, but something to do with orientation, and that seems to not be the case. But the one thing that I think is really fascinating about this is that, you know, I sort of said that the radio loud quasars were mostly up here, and look, you can see that that's the case. So this sort of quadrant up here has about 30% of the radio loud sources in it, but only 9% of the sources in this quadrant are actually radio loud, right? So you're completely dominated by radio quiet sources up here. And down in this corner, about 5% of the overall radio loud samples down here, but 99% of the things that are in this quadrant are actually radio quiet. And so we have these sort of really interesting trends, and you know, that may reveal something about what's going on with the radio. So one of the ways I like to sort of describe that is this. So if you make composite spectra, as I've shown here in the bottom right, of radio loud and radio quiet sources, you know, you can't tell the difference between these in terms of the optical emission line properties. So you know, if I don't tell you that the red are radio loud and the black are radio quiet, you know, really couldn't notice the difference. And so the way I usually describe that is, you know, it's generally not possible to use information outside of the radio to predict whether an individual quasar is going to be radio loud or not. All right, and I think I'll skip over this one. So you know, I'm not going to get into that in sort of more detail, but I'll leave you with the main conclusion that I've come to from this, which is that there's got to be some stochastic component to jet formation, right? So the fact that where the radio loud quasars live, the majority of objects are still radio quiet, means that there's something else going on that is causing the object to become, for the jets to be produced, that is not discernible in the optical UV. And so there's some kind of stochastic component, and it doesn't really matter whether you're tapping, the jets are coming from tapping the black hole spin or the accretion disk spin. And so one model I really like is that of magnetically arrested disks, which could potentially give you a way to sort of have that stochastic component to things. All right, so you know, the radio loud sources are pretty rare, but it turns out that if you look hard enough, almost every quasar is detectable in the radio. And so there's some interesting sort of trends that for the two demographics, so radio loud quasars versus radio quiet. So the radio louds here, now I'm plotting the UV luminosity versus redshift. And so the color coding here is the radio loud fraction. So, you know, I showed that the radio loud fraction can go from, you know, kind of 0% to the previous plot I showed was 9%, but, you know, even 25% here. It goes up with increasing luminosity and decreasing redshift. So there's a trend in the radio loud fraction here. But if we like ignore the radio loud objects, so these the big whopping things that are clearly jets, and just say, well, what is happening to the average radio flux in quasars. It's doing the exact opposite thing. So the lower luminosity objects and a higher redshift are the ones that are more likely to be emitting more radio. And Amy Rankin has another paper that's coming out that shows a similar kind of thing, but in the carbon-4 space. And so what we'd argue is that that's a sign that you have multiple sources of radio emission in these quasars. So in the radio quiet, we have sort of 4 different possibilities for producing that sort of average level of radio emission. Could be star formation, it could be the corona, it could be the winds that I've been talking about. So again, you know, the winds slamming into the ISM, producing a shock, or it could be sort of small scale jets that just aren't, you know, haven't grown or broken out of the sort of the host galaxy to reveal themselves. So star formation definitely makes a significant contribution. It would appear at least lower redshift. So this is work by Kimball and Condon, showing that for the really sort of whopping radio luminosity objects, those are dominated by radio emission that has something to do with the AGN directly. Whereas if you go to lower radio luminosities, there's evidence that some other component is taking over. Here illustrated by a sort of a star formation component that may not be sort of directly related to the AGN itself. So I'm interested in exploring whether winds, shocks from winds, these radiation line-driven winds could be producing radio emission. And so one of the problems with this previous study is that this is a low redshift. And so these are the luminosities in that sample. And based on what I was saying earlier about the winds, like you don't expect these luminosities to have winds. And so you don't expect the winds to be a contribution that you have to sort of tease out. So the question is, what happens here where the luminosities are such that the winds now start to be, are expected to be significant, never mind up here where the winds are almost certainly significant. And so we have done a little pilot survey. So this is 50 redshift 1.6 quasars at the luminosities highlighted here in the burgundy. And we observed them to 20 times the depth of first, right? And what we're trying to see is there a trend? So these objects here with large blue shifts, we think these things have stronger winds, and the things up here are going to have weaker winds. And what's interesting, we don't really see a strong trend there. We only detect, 44% of them, despite the fact that we've gone 20 times deeper than the deepest wide area radio survey, and there's no real strong trend in the carbon-4, and so that is kind of interesting, and definitely deserves further work in trying to understand what's going on there. And I think I'll skip over that one as well. So the bottom line here is that we need more work because right now we can't rule out either star formation or winds. And I took this slide from a very nice talk that Amy Rankin gave yesterday on her work with the LOFAR data and quasars, showing that it could be compact or weak jets, could be star formation, could be winds. We can't really rule any of those out. And so I'll encourage you to get her to tell you about her work there. And then, one of the problems is that we are making assumptions about star formation rates and therefore radio emission that come from extrapolating from the far infrared to star formation to radio. And it's possible that if the far infrared is not dominated by star formation, but it has a significant AGN contribution, then that sort of may complicate things as well. So I think this is a really interesting time in the study of radio emission from AGNs. And I think coupling our emission line diagnostics with the radio and infrared data is going to be a really powerful way to sort of tease out exactly what the multiple origins of radio emission are in both radio loud and radio quiet quasars. All right, so I want to finish up talking about sort of the next steps. And so regardless of whether you want quasars to study black hole physics or galaxy evolution or cosmic reionization, it helps to have more quasars. And so ignoring for a moment a tiny problem with the fact that LSST has no spectroscopic component, I'm going to talk about LSST. So LSST is now the legacy survey of space and time being conducted with the Simone Survey Telescope at the Vera Rubin Observatory as a joint project of the National Science Foundation and the US Department of Energy and international collaborators. And I think I have ticked all of the boxes that I'm supposed to cover, given that this is being recorded. So LSST is really going to be sort of SDSS on steroids. SDSS took about 8 years to cover some 10,000 square degrees of the sky, mostly once. LSST is going to be able to essentially redo the SDSS survey every 3 days. So we're going to have depths as deep as R of 27, with something like 800,000 visits over a 10-year period. And in addition to something like 18,000 square degrees illustrated here in the southern hemisphere, we're going to have sort of 4 to 10 regions of 10 square degrees that are going to go, maybe 10 to 100 times deeper, with many more observations for variability studies. And so one of the reasons to get involved in LSST now is that a lot of these parameters aren't fully defined. We're still running simulations and sort of seeing how well different science cases work in different simulations to try to decide what the parameters of the survey are. So if you're interested in using LSST for your science, this is a good time to get on board and make sure that the final choices are actually going to be useful for your science. All right, so our expectations for LSST is that it will identify something like 10 to 30 million quasars and AGNs using data only from LSST. And so like I said, it's really going to give you overwhelming statistics to do whatever kind of science you want with quasars and AGNs, from galaxy evolution to reionization to black hole physics. But we expect to detect about 300 million AGNs. The problem is that obscuration and sort of host galaxy dilution are going to hinder our ability to recognize those things as AGNs. So these are going to be, low luminosity AGNs where the host galaxy is now dominating the central engine. And so we have to basically take something that looks like a galaxy as opposed to something that looks like a star and recognize it as an AGN. We should be able to do that for about 100 million of the 300 million AGNs by combining with multi-wavelength observations. And so for those of you that work in the X-ray that are wondering what in the world is our problem, well, here's the issue, is that if you take bright X-ray sources, so X-ray brightness is going up to the right here, AGNs are largely dominating stars and galaxies until you get down to sort of relatively faint X-ray levels. That is not the case in the optical here at all. So now the brightness is increasing to the left, and so the brightest things are here and the fainter things are here. So the optically brightest sources in the sky are completely dominated by stars and then galaxies, and then the AGNs are kind of down here. All right. And so we are really stuck, if we just have LSST data alone, we're stuck trying to extract needles from a haystack. And so that means we really need to start taking better advantage of machine learning algorithms. And so these are some links at the bottom here to some things that I started producing. So this is just some base code to sort of use random forests and other things to do quasar classification. And then this is my current class that I'm teaching on big data physics, where I'm basically teaching machine learning to astronomers and physicists with the goal of doing things like science with LSST and IceCube and Dune and things like that. So one of the problems that we have is that we are going to need to be able to classify 40 billion sources. And we really only have a training set that's maybe 3 million objects. So we have spectra of something like 500,000 quasars and spectra of another 2 million, 2.5 million stars and galaxies. And those spectra aren't uniformly distributed through the parameter space that we need the training set to cover. And so we're really going to have to think outside the box on these things. And so one of the ideas that I like, that I'm keen about trying is described here, both in words in this cartoon. So I want to use autoencoders to cluster the unlabeled training data. So what do I mean by that? I'm going to take all 40 billion LSST sources, and I'm going to clump them together without knowing what they are. And I'm going to build a neural network to do that. And then I'm going to take the first layers of that neural network and then use them as the input to another neural network, where the training set now is going to not be all the data, but only the data that we have spectroscopy for, and then use that as our classifier. And so, we're going to have to sort of do next generation things like that. Yeah, fine. And so, you might say, well, what's an autoencoder? An autoencoder is how you make fake images of people or things, right? So yes, I'm teaching my class how to make deep fakes, not to subvert governments, but because it's actually really useful for astronomy. Okay, and so one of the things that we're able to do when we sort of move to machine learning algorithms, as opposed to just making cuts in color space or variability, is that we can sort of take a kitchen sink approach, really throw all of these things in together, right? So the color, the variability, astrometry, which I haven't talked about, multi-wavelength matching, morphology, and so on. Another thing we're going to have to do is sort of think about things probabilistically. So that is, we're not going to make catalogs of quasars. So that object isn't going to be classified as a quasar. This object isn't going to be classified as a star. So instead, this thing is going to go in as 90% quasar, 10% star. So when we're computing our luminosity function, we're going to add 0.9 instead of 1 when we add up the sort of number of quasars. And this thing is going to get classified as sort of 99% star, 1% quasar. Doing that is going to require some feature engineering, as it is called. So some things like colors are just going to get fed into the machine learning algorithm directly. The variability needs to be parameterized somehow. So we need to somehow basically describe the variability of these objects with a couple of numbers. And so the variability is particularly powerful, as I'm showing here. So we've got 4 different panels showing the same color plots. The one in the upper right here is showing quasars in blue and stars in red. And then the other 3 panels are showing different variability parameters. And what you can see is that the quasars and the stars have very different variability properties. And then if you were able to combine the colors and the variability together simultaneously to identify your quasars, you're going to do a much better job than just using sort of one at a time. All right. I think I'll skip over this, but we're just looking for different ways to sort of parameterize the variability that go beyond the damp random walk model that is common. And so I'll finish up with this and sort of try to tie the variability back to physics here, right? So I said, we have a really hard time measuring the accretion rates and the masses for individual objects. But it's possible the variability might actually give us some information here, right? So here I'm back to my slim disk cartoon, where on the right I have my X-ray corona sort of hidden behind this puffed up inner disk, and on the left my X-ray corona has a scale height that's larger than the puffed up inner disk. And so what that means here is that my optical variability that LSST is going to measure and objects like this is just going to be basically monitoring the variability of the accretion disk itself, the optical variability of the disk. Whereas if our object looks like this, so not only do we have the intrinsic variability of the disk, but we have this highly variable X-ray corona that's impinging upon the disk. And so we might expect the variability properties to change basically significantly from one side to the other, and sort of continuously going from things that look like this to things that look like this. So it may be that we actually can use the variability to tease out the actual accretion disk physics if we can do a good job parameterizing the variability in a way that is going to reveal that information. Okay, so I'll largely finish up here and just sort of say, the way we're going to do selection in LSST is to combine all these things together. We're going to take colors and variability, and I didn't talk about the astrometry, but basically simultaneously take all these different types of data and feed them into machine learning algorithms to do the best job we can finding all the AGNs and quasars. And so I'll draw to conclusion here. I like to give graphical conclusions. So the first one is that quasars aren't uniform, right? So we can't just have one static cartoon that describes quasars because there's a large range of properties, and things are actually really changing as you change the mass and accretion rate. And that's illustrated here by the change in the ability to drive a wind off the accretion disk. So I argued that even if you can't determine the mass and the accretion rate directly, you can empirically determine it from the emission line properties. That is, you can at least compare things that have high mass, low accretion rate to things that are opposite by using these emission line diagnostics. And those kind of techniques are really going to hold great promise for deriving quasar physics from their spectra, not just masses and accretion rates, but also what's going on in the radio. And so lastly, so LSST is going to find about 100 million AGNs. And it's going to be aided by novel data features, including the variability and machine learning as the basis for our algorithms. So I'll stop there and thank you for your time and listening, and happy to take whatever questions people have.
Fantastic. Thanks so much, Gordon. You can't obviously hear the raucous applause that's going on in everybody's dining rooms or living rooms or whatever, but it's happening.
Indeed.
You've got to know it's happening. So I'm just going to stop the recording and we can move on to the fun that is the question and answer session.